much for showing up this bright and early. I'm glad there's a lot of coffee, you guys stay awake, and hopefully an exciting presentation too. So I'm talking about our latest results from our new biogeochemical model in the Gulf of Alaska. And to start up with, I would like to thank my co-authors, and especially Kate Hedstrom, who has been essential for the development of the model. The motivation to create such a model, a biogeochemistry model for the Gulf of Alaska, is to study ocean acidification and climate change in the Gulf of Alaska, and also to get a better understanding of just the current state of the inorganic carbon chemistry and the natural drivers that drives that system. As we all know, there are several species and organisms in the Gulf of Alaska that have been shown to be potentially negatively affected by ocean acidification, such as cannon crabs, clams and mussels, and pteropods. And there just has been a recent study actually come out in global change biology showing that even coho salmon may be potentially directly negatively affected by ocean acidification. Low pH environments, high CO2 affect their olfactory systems, and they have impairments in their behaviors. So, as I said, I'm not just interested in ocean acidification and climate change, but also in how natural drivers, physical and biological drivers, change the inorganic carbon system. And some big drivers within the Gulf of Alaska that I'm going to study over the next few weeks are freshwater input. Freshwater input in the Gulf of Alaska has a huge effect on the physical oceanography, especially in the nearshore waters. It drives the Alaska coastal current. Then it also has a huge impact on iron. It brings in a lot of iron, triggering a lot of big phytoplankton blooms in spring and also later in the summer. But it also has a direct impact on the inorganic carbon chemistry by decreasing the pH and also the carbonate ions in the system, which then has potential harmful effects on these organisms that I showed before. Another big driver is downwelling, or better, the relaxation of downwelling. So downwelling generally happens between September and May, and it peaks around January. And then in June, once it relaxes, it actually allows high CO2 water come up onto the shelf, causing low carbonate ion concentrations on the shelf and also low pH environments. Now diving right into our model, we modeled the last 33 years using the Regional Ocean Modeling System and COBALT, which is a carbon-based model. We used explicitly forced coastal freshwater discharges to force the model at its boundaries, because we all know we have a lot of mountains around the Gulf of Alaska that change the inorganic carbon chemistry through their freshwater input. And so that's output from a hindcast simulation based on work that was done by Hill and Beamer at OSU. And so we have intra-annual variability, but also the impacts of climate change in that forcing. And then if you're more interested in the rest of the model setup, please come and talk to me later. I don't want to bore everybody. Let's dive into comparisons between the model and observations. Here I'm using observations from the Ocean Acidification Research Center at UAF, from a cruise that they performed in September 2008. So that's a snapshot of the system, and I'm comparing it, which is a little unfair, to a monthly output from my model in September 2008. And as you can see, it really represents the overall structure of the water column of arachnite saturation state pretty well. It shows the undersaturation of arachnite on the shelf. It shows the saturation horizon at around 100 meters offshore, as is shown by observations as well. We do have a little bit of issues, actually, because we are underestimating the saturation state at the surface offshore a little bit. And this has to do with the fact that we're not able to really represent the strong phytoplankton blooms that also happen later in the season. Now, here I'm showing a seasonal cycle of the arachnite saturation state, which is a measure of carbonate ions on the sea shelf just off Seward. And the model is nice because you can kind of look at not just snapshots, but also the seasonal variability throughout the year. And this, the model suggests that the aragonite saturation state is undersaturated about 6 months out of the year, which starts the dissolution of a lot of aragonite structures. And it's oversaturated in spring, which is also confirmed by observations from the Seward land cruise in May. So now if you add the salinity seasonal cycle to it, you can see as soon as salinity increases in June, the aragonite saturation state decreases, and this is a sign of the influence of the relaxation of downwelling on your inorganic carbon chemistry, or the aragonite saturation state on the seafloor near Seward, and how much of this low aragonite saturation state is actually due to remineralization still needs to be analyzed. Now let's have a look how this changed over the last 33 years. On the left, you can see an annual mean of the aragonite saturation horizon in 1980. And this the aragonite saturation horizon is basically the depth where the aragonite saturation state is equals 1. And then on the right, you see it for 2013. Wherever you see black colors along the shore, that means that the aragonite saturation horizon has not shoaled onto the shelf yet. Whereas where you see orange to blue colors, the aragonite saturation state or horizon is between 150 and 200 meters, and everything in orange and red means that it has shoaled already up to like 50 or 100 meters. And what I want to point out here is that, especially around Kodiak here, and then also along the Aleutian chain, and over in Cordova and south of Yakutat, the aragonite saturation horizon has already shoaled into the upper 50 meters, which could have large implications for the ecosystem there. Now, as a next step, I would like to look at the transect of Seward to get a better understanding of the aragonite saturation state across the profile. Here again, on the left, you see an annual mean of 1980, and then on the right, there's an annual mean of 2013 showing the aragonite saturation state. Everything in orange-red is below the aragonite saturation state of 1, and then yellow to blue means between 1 and 2. And one thing that I really want to point out is that in 1980, you already have sustained aragonite undersaturation on an annual mean across the entire shelf. Another important feature is that back in 1980, the aragonite saturation state was still above 1.5 up to about 2 in onshore regions at the surface and in the upper water column. And now in 2013, the model predicts that the aragonite saturation state is below 1.5, which may have already affected theropod populations in that area negatively. And Nina Bednarsek is going to talk about this in a couple of talks later this morning. And another interesting feature on this figure here is that aragonite saturation state is as low as 0.5 at 80 meters, and that isoline was not seen at all in 1980. So very corrosive waters coming up into the upper 80 meters of the water column. Now I want to look at the evolution of aragonite saturation state over the last 33 years, looking at different stations here. GAC1, which is very close to the shore at the surface and at 100 meters, and GAC10, which is about 160 kilometers offshore, still above the shelf and at 100 meters. And concentrating first on that offshore station at the surface, it shows very strong seasonal variability of about 1.6 aragonite saturation state units and a significant decreasing trend at a rate of about 0.06 per decade across the last 3 decades. And then looking at the next station at the surface, very similar picture except for the aragonite saturation state is a little bit lower, which probably has to do with the freshwater input near shore. And another interesting point that I want to point out is that nearshore surface alkalinity has also significantly decreased over the last 3 decades. And so that means that there is already an effect of climate change that enhances ocean acidification as well. Now looking at the nearshore 100-meter station, the seasonal variability is much smaller, which is expected because there's not so much the influence of biology, but also freshwater input, but a very similar significant trend, and all waters are still oversaturated. And then an interesting feature is offshore, about 160 kilometers off the coast, you can see that aragonite undersaturation already happened during some years around the 1990s, and now in 2013 the model says that it's about undersaturated about 6 months per year, so half of the year. Now coming to the conclusions already, the seafloor near Seward is aragonite undersaturated about 6 months out of the year. Seasonal aragonite undersaturation on seafloor is mainly driven by the relaxation of downwelling. The aragonite saturation state is decreasing by about 0.06 aragonite state units. Some of it is driven by increased freshwater input in nearshore areas. And another interesting feature, comparing this rate to the US West Coast, to model output from there, it shows that our rate of aragonite saturation decrease is only half as fast as the one that they found in the California current system. However, this has likely to do with the buffer capacity, and we can talk about this later on if you're interested. So the buffer capacity is much lower in the Gulf of Alaska, but that also means that probably the pH decrease is much faster in our area, which would have huge implications for the salmon population. And then, oh, I forgot my last point. Conditions in nearshore upper water column have already become harmful for pteropods, and as I said, Nina is going to talk to you about this a little bit more later. And as a last slide, I would like to thank NSF for funding this study, the development of the model, but also to fund our first Girls in Icy Fjords expedition. 2017, we were able to bring 9 girls out to Bear Glacier for 8 days. We camped near the glacier. We did science and art, we sea kayaked, and it's all part of the bigger organization Inspiring Girls Expeditions. And I want to do a little bit of publicity here. The applications are open until February 1st, so if you know any high school girls between 16 and 17 years old who would like to participate in one of our 7 programs that take girls either to glaciers or to the ocean or on rocks, please let them know to apply. Thank you. Any questions? Okay.
Yeah, it's time for a couple of questions.
Too much information at 8 o'clock in the morning, sorry. Yeah, just talk to me later. Thank you.